We're going to manage to show that the Schur functions form a basis of the homogeneous degree D symmetric functions by comparing them to the monomial basis directly. So recall that we defined the matrix H lambda to be the matrix that has little h lambda 1 here, and then little h lambda 1 plus 1, little h lambda 1 plus 2, up to little h lambda 1 plus L minus 1. So letting lambda be lambda 1 through lambda L. And then we put h lambda 2 in the 2, 2 position. Subtract 1 from the index here, add 1 to the index here, then add 2, etc. Then I guess on the end we get h lambda 2 plus L minus 2. And then we put h lambda 3 in the 3, 3 position. Subtract 1 from the index there, subtract 2 from the index here. Increase the indices by 1 all the way across. And then I guess we get h lambda 3 plus L minus 3. Then in the last row we have h lambda L minus L plus 1 and h lambda L minus L plus 2, h lambda L minus L plus 3, and in the last position we've got h lambda L. I'm going to use D for the degree here. Now we define the Schur function. S lambda is the determinant of the matrix H lambda. Now, of course, determinant of the transpose of a matrix is determinant of the original matrix. And this is going to be more convenient temporarily. So for the moment we're going to use S lambda as the determinant of H lambda transpose. Transposing is just going to make the pictures come out nicer. Now the following interpretation of S lambda as sum of weights of non-intersecting path families in a planar network is due to Gessel and Viennot. So let's draw the planar network that's going to correspond to that. It's a little bit messy to draw in general, but hopefully I'll be able to get this. Maybe I'll leave the matrix there. So we've got horizontal edges oriented from left to right, vertical edges oriented down. And let's say we have n variables. Now, I'm going to actually have the planar network be infinite going upward. That'll just be convenient for the moment. And then let me label some sources here. Now, every time we have a source on the left, we go across to a potential sink over here, and then count down lambda 1 and actually put the corresponding sink there. So for S2, we go over and then we go down lambda 2 and put the corresponding sink there. That'll be T2. For S3, we go over, go down lambda 3 and then put the corresponding sink 3 there. See if I can do one more. S4, I won't put it all the way over on the end, but go down lambda 4 and put the corresponding sink there. So you can check that this rule gives us a planar network whose path matrix is the transpose of H lambda, which is just as good because the determinant of the transpose of H lambda equals the determinant of H lambda. So to be less abstract, let's do an example of this. So let's look at 3 variables and a partition of 3. So for example, D and N are both 3, lambda equals 2, 1. So S1 is here. We'll go down lambda 1, which is 2, and put a sink there. And then for S2, we'll go down 1 and put a sink there. And let me draw 8 copies of these because we're going to find 8 path families that are non-intersecting from these sources to those sinks. I guess they're basically a box divided into 6. So that's 7, and we need 8. Alright, so the first path could, the first variable could go down as the x1 edge, so it could go down x1, x1, and then over. And then the second path could go down, let's say, on the x2 variable. It can't go down on x1 because then they're going to crash. So again, we'll take x1, x1, and then the second path can go down on x3 there. Then the next thing that this path can do is we could go down x1 and then x2. The third path can't go down x1, but it can go down x2. Or if the bottom, the bottom path goes down x1, x2, then the top path can go all the way over to x3. And then what else can we do with the bottom path? Bottom path could go x1, x3. The top path could go on x2 or x3. The bottom path could go on x2 and x2. Top path can't go on 1 or 2, but it can go on 3. And then the bottom path could go on x2 and x3, because if we go on x2, x2 again, there's nothing else the top path can do except for x3. And then the top path can go on x3. So we can summarize these paths just by recording the indices. Summarize these path families by recording the indices. So path 1 went on x1 and x1, path 2 went on x2. Path 1 went on x1 and x1, path 2 went on x3. Here path 1 went on x1 and x2, path 2 went on x2. Here path 1 went on x1 and x2, path 2 went on x3. Here path 1 went down x1 and x3, path 2 went down in x2. Path 1 went down x1 and x3, path 2 went down in x3. Here path 1 went down on path 2 and path 2. Path 2 went down at x3. And here path 1 went down variables x2, x3, and then path 2, x3. Now the coefficient of mu in S lambda equals the coefficient of x1 to the mu1, x2 to the mu2, which is the number of path families number of non-intersecting path families, of course, of weight x1 to the mu1, x2 to the mu2, etc. Now the resulting tableau here, the shorthand, have some properties that are important if we want to count them without actually drawing all the path families. So the Young tableau recording the non-intersecting path families have the properties of their column strict and that's because the first step down of path 2 can't be in the same variable as the first step down of path 1, or they crash. Similarly, the second step down of path 2, well, there isn't one in this example, but if there were, it couldn't be in the same variable as the second step down of path 1. So the jth step down in path I must be on an edge weighted by a variable with greater index. than the jth step down in path I minus 1. So that's going to force us in the tableau always to strictly increase as we go up in columns. And then a second property, I guess I can erase these path families. Second property is row semi-strictness. So column strict means going up in columns. The numbers have to increase. Strict increase. And row semi-strictness means weak increase to the right in rows. And that's simply because after we take an edge down, since all the edges go down and to the right, once we take a variable xi, we could either take xi again or x something greater, but we can never take x something less. So each step down is on an edge. Weighted by a variable with index greater than or equal to the previous variable. All right, there's a name for these numbers that come up. We define k lambda mu, which is called the lambda mu Koska number. To be the number of column strict, row semi-strict. Actually, this combination of properties is called semi-standard. Number of semi-standard Young tableau of shape lambda and content mu. So content mu is mu1 ones, mu2 twos, etc. Semi-standard means row semi-strict and column strict. All right, now to prove that the Schur functions form a basis of the Z module of homogeneous degree D symmetric functions, we're going to show that the matrix of Koska numbers is unitriangular and therefore invertible over the integers. So we have k lambda lambda equals 1 and k lambda mu equals 0 if mu is not less than or equal to lambda in the majorization order. Also called the dominance order. And I think I go back and forth calling it one or the other, but they're the same thing. So the proof is there's a unique way to fill a Young tableau of shape lambda with lambda 1 ones, lambda 2 twos, etc. Well, technically we're filling a Young diagram because before we put numbers in it, it's called a Young diagram. So that the resulting tableau, once we put numbers in it, it's called a tableau. Is semi-standard. So row semi-strict and column strict. And that unique way is to put lambda 1 ones in row 1, lambda 2 twos in row 2, lambda 3 threes in row 3, etc. Alright, so that shows that the Koska number k lambda lambda is 1. Now let's suppose that mu is less than or equal to lambda in the dominance order. And for some index j, we have that mu1 plus, so the jth partial sum of mu is greater than the jth partial sum of lambda. But then mu1 ones, mu2 twos, etc. up to mu j j's won't fit into a Young diagram. Well, into the first j rows. Of a Young diagram of shape lambda. So we would have to put some of those letters into row j plus 1. But if we have j different letters and we pack them j plus 1 high in some column, then that column will have a repeated letter. And therefore, the tableau cannot be semi-standard. In particular, it can't be column strict. So the corollary is that the Schur functions the set of Schur functions forms a basis of the z module of degree d homogeneous symmetric functions. And that's because the transition matrix relating Schur functions and monomial symmetric functions is unitriangular. It's got integer entries, all ones on the diagonal, zeros above the diagonal or below the diagonal, depending how you list the basis. Therefore, it's invertible over the integers. And then a second corollary is that the homogeneous symmetric functions form a basis also, because we already know that they're related to the Schur functions by a unitriangular transition matrix. So now we've got the bases of the degree d homogeneous symmetric functions. Well, some that we know are monomial symmetric functions, elementary symmetric functions, power sum symmetric functions. Oops, power sum symmetric functions are not a basis of that unless we add rational numbers. So homogeneous symmetric functions and Schur functions. And bases of the degree d homogeneous symmetric functions with rational coefficients are all of these and the power sum symmetric functions. The end.